Okay, so today we need to talk about the functional limit definition, which is often called the epsilon delta definition of the limit. So this is limits in the sense of calculus 1, where you've got some function f of x, you're letting x approach c, and you're trying to figure out what f of x approaches as x approaches c. So the formal definition, there's kind of a lot to it. It's very similar to the sequential limit definition, but instead of finding a capital N past which the sequence is close enough to its limit, we have to find a delta so that if x is that close to c, then f of x is close enough to our target L. All right, so the full version, this is kind of using the abbreviated notation. The full version is in the text or in the notes. But we say that the limit of f of x as x approaches c equals L if for every epsilon bigger than 0, so some real number, we typically think of it as a small real number, but for every epsilon bigger than 0, there exists some delta, which often depends on the epsilon. That's also a positive real number, so that if I am within then I know that my function values are closer than epsilon to the target L. So a kind of English version of this is that we can make f of x get as close as we like to L by taking x close enough to c. Now that's a little bit more precise than what you might have remembered from calculus 1, where we might say something like f of x gets close to L as x gets close to c. Right? So that's not nearly precise enough to make any progress with theorems and so on. But a better version of that is that not just that f of x is getting close to L, but we can make f of x be as close as we like to L. So this phrase is important. And that phrase is governed by our choice of epsilon. Epsilon tells us how close we would like f of x be to L. So if we can make that happen by taking x not just close, but x close enough to c, if we can always do that, then we have established the limit. And this x close enough to c is governed by my delta. Right? So epsilon is our error tolerance for how close f of x needs to be to capital L. And delta is the response, how close x needs to be to c in order to make that happen. Right, so that's kind of what's going on in the definition. We're going to now do an example, and I'll do a more complicated example in the video immediately following this one. Hopefully you'll recognize the structure of the proofs we did using the definition for sequential limits. Right, so the task for our example is to show, using the definition, that the limit as x approaches 4 of 3x plus 5 turns out to be 17. Now it shouldn't be a surprising result, right? From calculus we're used to just plugging in x equals 4. We would get 3 times 4 is 12, plus 5 is 17, so this seems like it ought to be the limit. But if it is, we should be able to prove it. So let's take a look. The structure is identical to the sequential limit proofs. We let epsilon be bigger than 0, and then we consider the thing we need to make small. In this case, it's whatever f of x minus L is. F of x is 3x plus 5. L is 17. So we plug those in. Now inside the absolute value, I can do a little bit of arithmetic. And that's going to give me, let's see, 3x minus 12, and then if I pull the 3 out, I get 3 times x minus 4. Now this is a place where you can kind of recognize that you're doing something right, because the thing we have control over is how close we take x to 4, right? 4 is the c, and we need to show that if we get close enough to 4, then we can make our limit be, we can make our function be within epsilon of 17. So to see x minus 4 appear is good news, because that's the thing we can make small. And the idea is if we make that small enough, then the original expression f of x minus L will also be small enough. So we want to make this less than epsilon, and we do it with our control of this x minus 4 term. So a little bit of algebra. Let me just write it this way. So this happens when x minus 4 is less than epsilon over 3, right? I've just divided both sides of the desired inequality by 3. And that reveals our delta. That's how close x needs to get to 4 in order to make 3x plus 5 within epsilon of 17. So then to formally finish up the proof, we would write let epsilon be bigger than 0. And take delta sub epsilon equal to epsilon over 3. That's also bigger than 0. Then if x minus 4 is less than epsilon over 3, we have f of x minus L is less than 3 times epsilon over 3 equals epsilon as required. Right, so just like in sequential limits, take an epsilon that's positive, consider the thing you have to make small, do some algebra on it until the thing you know you can make small appears. Sometimes that algebra is harder than other times. And then use the fact that you can make that thing get small to find the delta that would be required. Right, and then the rest of it, so that's like the work really in the proof, and the rest is writing it up so that it follows the definition. One thing that we haven't talked about that is mentioned a little bit in the notes, or is one of the things to fill in the notes, and that is the purpose of this greater than 0 for our x minus c term. And that is there to rule out x being equal to c, right? It's just a convenient way of saying x needs to get close enough to c, but we're not actually concerned with what happens at c, right? Remember, limits are about what happens when x gets near c, not actually what happens at c. If you're worried about what happens at c, that's a question of continuity, and we'll get there in the next section. Right? But for now, just think of that greater than 0 as a sort of convenient way of ruling out x being equal to c, which is what we want for a limit. All right, so next up, let me do one where the algebra is a little bit more involved.